Let's now have a detailed look at the system architecture of SONiC. SONiC system architecture comprises of various modules that interact among each other through a centralized and scalable infrastructure. This infrastructure relies on the use of a Redis database engine, a key-value database to provide a language-independent interface, a method for data persistence, replication, and communication among all SONiC subsystems. By relying on the publisher-subscriber messaging paradigm offered by the Redis engine infrastructure, applications can subscribe only to the data views that they require and avoid implementation details that are irrelevant to their functionality. SONiC places each module in an independent Docker container to keep high cohesion among semantically affine components, while reducing coupling between disjoint ones. Each of these components are written to be entirely independent of the platform-specific details required to interact with lower-layer abstractions. As of today, SONiC breaks its main functional components down into the following Docker containers: DHCP Relay, Pmon, SNMP, LLDP, BGP, TeamD, Database, SWSS, and SyncD. The following diagrams display a high-level view of the functionality enclosed within each Docker container, and how these containers interact among each other. Notice that not all SONiC applications interact with other SONiC components, as some of these collect their state from external entities. We are making use of blue arrows to represent the interactions with the centralized Redis engine, and black arrows for all the others. This diagram describes the whole disaggregated architecture of the SONiC networking operating system and the interactions between all of the components, starting at the hardware level all the way up through the kernel and user space. At the bottom of the diagram, we see elements which are related to the physical hardware, that is the switch, running SONiC. Those are things such as fans, power supplies, or LEDs informing us about the status of each port. Two other crucial elements of each network device are transceivers, which provide external connectivity to the system, and the ASIC, a microchip which is at the heart of each network device and facilitates high-speed data forwarding in silicon through all of the switch ports. All of the hardware elements have their respective drivers, which operate in the kernel space and enable communication between those hardware components and applications running in the user space. For example, ASIC SDK and SAI API running in the SyncD container work with the ASIC driver residing in system's kernel and allow exposure of the switch front panel ports to other parts of the system, such as the application providing LLDP or DHCP relay functionality. Other kernel drivers work in conjunction with daemons in Pmon container and make sure the switch does not overheat by reading values of temperature sensors and controlling the speed of hardware fans cooling the switch. Moving one layer up, we enter the user space, which is where most of the software elements reside. Again, we see the Redis server holding databases crucial to the proper operation of SONiC. All of the user space elements interact with various configuration and state databases running within the database container. In the following slides, we will go through each of the elements depicted on this diagram and explore in detail what their functions are. The TeamD container runs link aggregation functionality in SONiC devices. TeamD is a Linux-based open source implementation of the LAG protocol. The TeamSyncD process allows the interaction between TeamD and southbound subsystems. The Pmon container is in charge of running SensorD, a daemon used to periodically log sensor readings from hardware components and to alert when an alarm is signaled. Pmon container also hosts fan control process to collect fan-related state from the corresponding platform drivers. The SNMP container hosts SNMP features. There are two relevant processes within this container. SNMPD is the actual SNMP server in charge of handling incoming SNMP ports from external network elements. The SNMP agent is SONiC's implementation of an AgentX SNMP sub-agent. This sub-agent feeds the master agent SNMPD with information collected from SONiC databases in the centralized Redis engine. The DHCP relay container hosts a DHCP relay agent that enables the relay of DHCP requests from a subnet with no DHCP server to one or more DHCP servers on other subnets. The LLDP container hosts the LLDP functionality. These are the relevant processes running in this container. LLDP is the actual LLDP daemon featuring LLDP functionality. This is the process establishing LLDP connections with external peers to advertise and receive system capabilities. LLDP syncd is the process in charge of uploading LLDP's discovered state to the centralized system's message infrastructure, the Redis engine. By doing so, LLDP state will be delivered to applications interested in consuming this information, for example SNMP. LLDP Manager is the process that provides incremental configuration capabilities to the LLDP daemon. It does so by subscribing to StateDB within the Redis engine. The BGP container runs one of the supported routing stacks, Quagga or FRR. Even though the container is named after the routing protocol, in reality these routing stacks can run various other protocols, such as OSPF, ISIS, LDP, etc. BGP container functionalities are broken down as follows. BGPD is a regular BGP implementation. Routing state from external parties is received through the regular TCP and UDP sockets and pushed down to the forwarding plane through the Zebra FPM syncd interface. Zebra acts as a traditional IP routing manager. That is, it provides kernel routing table updates, interface lookups, and route distribution services across different protocols. Zebra also takes care of pushing the computed forwarding information base down to both the kernel through the netlink interface and to southbound components involved in the forwarding process through Forwarding Plane Manager Interface (FPM). FPM syncd is a small daemon in charge of collecting the FIP state generated by Zebra and dumping its content into the application DB table AppleDB sitting within the Redis engine. The database container hosts the Redis database engine. Databases held within this engine are accessible to Sonic applications through a Unix socket exposed for this purpose by the Redis daemon. These are the main databases hosted by the Redis engine. AppleDB stores the state generated by all application containers, routes, next hops, neighbors, etc. This is the southbound entry point for all applications wishing to interact with other Sonic subsystems. ConfigDB stores the configuration state created by Sonic applications, port configurations, interfaces, VLANs, etc. StateDB stores key operational state for entities configured in the system. This state is used to resolve dependencies between different Sonic subsystems. For example, a lag port channel defined by the TMD submodule can potentially refer to physical ports that may or may not be present in the system. Another example would be the definition of a VLAN through VLAN Manager D component, which may reference port members whose presence is undetermined in the system. In essence, this DB stores all the state that is deemed necessary to resolve cross-modular dependencies. ASICDB stores the necessary state to drive the ASIC's configuration and operation. State here is kept in an ASIC-friendly format to ease the interaction between syncd, see details further below, and ASIC SDKs. The counters DB stores counters and statistics associated to each port in the system. This state can be utilized to satisfy a local CLI request or to feed a telemetry channel for remote consumption. The switch state service, or in short SWSS, container comprises of a collection of tools to allow an effective communication among all Sonic modules. SWSS mainly focuses on offering mechanisms to foster communication and arbitration between all the different parties. SWSS also hosts the processes in charge of the northbound interaction with the Sonic application layer. These daemons are typically identified by the naming convention being utilized. They all end in syncd. Port syncd listens to port-related netlink events. During boot up, port syncd obtains a physical port information by parsing system's hardware profile config files. In all these cases, port syncd ends up pushing all the collected state into AppleDB. Attributes such as port speeds, lanes, and MTU are transferred through this channel. Interface syncd listens to interface-related netlink events and push collected state into the AppleDB. Attributes such as new changed IP addresses associated to an interface are handled by this process. NAsyncD listens to neighbor-related netlink events triggered by newly discovered neighbors as a result of ARP processing. Attributes such as the MAC address and neighbor's address family are handled by this daemon. This state will be eventually used to build the adjacency table required in the data plane for Layer 2 rewrite purposes. Once again, all collected state ends up being transferred into AppleDB. The above processes act as state producers as they inject information into the publisher-subscriber pipeline, represented by the Redis engine. But there is another set of processes acting as subscribers, willing to consume and redistribute all this incoming state information. This is the case with the following daemons. Org-Agent is the most critical component in the SWSS subsystem. Org-Agent contains logic to extract all the relevant state injected by syncd daemons, process and message this information accordingly. Finally, push it towards its southbound interface. This southbound interface is yet again another database within this Redis engine, the ASICDB. So as we can see, Org-Agent operates both as a consumer, for example for state coming from AppleDB, and also as a producer, for state being pushed into ASICDB. Inf-mgrd reacts to state arriving from AppleDB, ConfigDB, and StateDB to configure interfaces in the Linux kernel. This step is only accomplished if there is no conflicting or inconsistent state within any of the databases being monitored. Refer to the above database container section for examples of this undesired behavior. VLAN manager reacts to state arriving from AppleDB, ConfigDB, and StateDB to configure VLAN interfaces in the Linux kernel. As in inf-mgrd's case, this step will be only attempted if there is no dependent state conditions being unmet. And finally, there's the syncd container. Its goal is to provide a mechanism to allow the synchronization of the switch's network state with the switch's actual hardware. This includes the initialization, configuration, and collection of the switch's ASIC current status. These are the main logical components present in syncd container. At compilation time, syncd links with the ASIC SDK library provided by the hardware vendor and injects state to the ASICs by invoking the interfaces provided for such effect. Syncd subscribes to ASICDB to receive state from SWSS actors and at the same time registers as a publisher to push state coming from the hardware. SAI API. The Switch Abstraction Interface SAI defines the API to provide a vendor-independent way of controlling forwarding elements, such as a switching ASIC, an NPU, or a software switch in a uniform manner. And finally, there's the ASIC SDK. Hardware vendors are expected to provide a SAI-friendly implementation of the SDK required to drive their ASICs. This implementation is typically provided in the form of a dynamic linked library, which hooks up to a driving process, syncd in this case, responsible of driving its execution.